Oh. All right, great. Hello. All right, so yeah, apologies for the background noise. Let me. I thought we disabled the waiting room. That's okay, good. Gonna see if more people will come and like just finish putting on the last touches, but today will be a glorious day of horrible bashing. And yeah, we'll see that we can't. We'll see how we can do. So yeah, with me, of course, is Andrew Kai, who will be our TA, problem solver extraordinaire. All right. Yeah, so everybody's favorite subject. All right. Please don't spam me when I'm trying to teach, by the way. Like, yeah, I'm just going to say that I'm going to be like a bit harsher on like people who like aggressively spam my chats. So like if you do it enough, then I will remove the person in question. And enough will be decided by me. So if you don't want to take that risk, then just don't spam me, please. Hello. Okay, recording is started. Okay, great. We are going to do Counting Strategies 1 today. So let me get the whiteboard shared. And I want people to just tell me general counting strategies. Like, what are some methods that you might use when solving counting problems? All right, and while I was writing that, the chat exploded. So let me go back and do it. Fingers, yes. Counting on fingers is really good. It's a really great way to make sure that you don't make mistakes. Counting, yes, that's what we're doing. Casework, yes, we are going to want to investigate casework and how to set this up efficiently or efficiently enough. Counting by 5, that's nice. Counting by 1. Binomials, yep. They're typically written as n choose k. This is going to be the bread and butter of a lot of like the smaller computations. So completely mastering this will be really important. Complementary counting, excellent. Yeah, this is a great way of simplifying your work. Counting by 10, yes. All right, thanks. Pigeonhole principle is not really exactly something that you use when you're trying to count something. It's something that you do with the counts. Stars and bars, I will not get into that today. There's plenty of more general approaches that we need. Gen functions, recursions. Generating functions was covered in a previous seminar and is really advanced. Recursion will be done on Wednesday, so you guys should come if you want to see that. All right, the addition principle. Yeah, that's a great way of thinking about casework. Addition principle and the multiplication principle. Great. We've just covered all the main areas that I'm going to try and knock out during today. Great. So we have all these ideas and they could be used. They're ideas that can be used to solve things. Bases, I don't know what you mean by that or what constructive counting is. I feel like that's kind of just counting. Multiplication property. Geometric probability is not really combinatoric, not really like something that you use to count, unless you want to get into a discussion on infinity, which I do not. But probability will be a different day. All right, so yeah. So the important thing when solving like any counting problem is to 1, figure out what the structure is, 2, figure out if we can use any one of these principles, to count that structure. So I want everybody to just keep these in mind. Multiplication principle, we're going to be hitting that first, then complementary accounting, just as a side, and then a lot of casework at the end, because setting up effective casework is 90% of the problem sometimes. So what I'm going to do is I am going to now share this. All right, and this is, some people know it as the multiplication principle. So, other people, I like to think of this as just like independence. But here are some simple example problems, just like idiomatic counting things. So think about these for a minute. If you have answers, feel free to send them my way. I won't really be whiteboarding this because they're simple enough. Another topic, another name for this section is just like exploiting some sort of symmetry. And I'm glad that starting with this example will allow me to touch on a certain subtlety involved. So yeah, let me try annotating. Annotating has been known to crash. Has been known to crash. Oh, huh. Why am I not able to? That's unfortunate. Okay, I guess we will go to whiteboard. All right, I do not believe that anybody has given me the final answer for question 2.1, like the exact number answer. Or okay, one person has. Yeah, 2.1 is a bit trickier than you might think. Oh no. Sorry, managing lots of screens can be difficult. Okay, so I'm gonna go to the whiteboard right now. A lot of people have sent me answers and not all of them are correct, which is good. Okay, so for the first one. For the first one, 4 digits and you have things. So the main idea here in 2.1 is that each digit is completely independent. So we can look at these separately, and then what independence does is it allows us to multiply them. So second and fourth digits. So this one has to be odd. This one has to be odd. So how many possibilities are there for this digit? 5. And this digit's also 5. How many possibilities are there for this digit? This third digit right here? There are 10. Yeah, because we don't have any restrictions. And now how many possibilities for this digit? Some people are saying 10, but a lot more people are saying 9. And this is tricky. This is something that you're going to have to know for math problems. 4-digit numbers cannot begin with 0, because then it would be a 3-digit number, or even a 2 or 1-digit number. So you have to like do that extra bit of work to make sure that you start here. So we multiply all these together. And the reason that we can multiply is because they're independent. All right. And the way that you determine independence is if I change this, does that affect what I do here at all? And conceptually, the answer should be no. So this equals, I think a lot of people said 2250. I'm going to trust you all on that. And all right, cool. That's one problem down. So now we have a similar setup. And now we're answering the question, how many ways can we do it so that these 4 digits are distinct? And I'm just going to go straight ahead and do this one because it's a bit trickier. And for the reasons you might not think. Okay, so there's no longer independence, because what I mean by that is I can't, the possibilities for this change if I start with a 1 versus starting with a 2. But regardless of that, we can still extract some structure. The morally correct way of like thinking about the structure is drawing a tree. And basically through this tree, you just like outline possibilities, and then you notice that the number of branches is going to be the same. So let's see. How many ways are there to choose this? Let's say we're choosing them from left to right. There's 9 ways. All right, so now let's say we've chosen this. Let's say we put like a 3 in there. How many ways are there to choose this one now? There are also 9. Now, why is there not 8? Well, we've lost one of the choices because of this right here, but we've also gained 0 right here. Yeah, exactly. So they're also going to be 9. Let's say let's just make it 0 in the fact. I haven't computed the answer actually, so it could be. All right, but in any case, we've taken away 2 possibilities. So we know that there are 8 possibilities here, regardless of what they are. All right, and the important thing is that these possibilities could be different depending on what these 2 numbers are. But the counts of the possibilities is constant. Then, of course, the final one is 7. 9 times 9 times 8 times 7. What is that? 81 times 56. I'm going to trust you all on that. That's like, what, 56 plus 448. 4480. Yeah, 4536. Spectacular. So what I want everybody to remember here is that the independent things were these digits. All right, changing these when we go by this way doesn't really change the possibilities, the number of possibilities. And another thing that I'd like to emphasize is that we started from the left and worked our way right. And this is actually really important. And what we did is we started with the most conditions and we went to ones with less conditions. And this is a good approach thing to keep in mind. Because what if we started from the right and went to the left? Then we'd have casework, because what if 0 was taken here or 0 was not taken? You are not allowed to annotate. All right, if you annotate, I will. Yeah, I'd rather not get into that. So, yeah. Oh, so this is constructive counting? Yeah, other people call it the rule of multiplication. And yeah, it's really useful because this allows us to break down really big problems into simple multiplications. And that's a lot of like how we simplify this. So I'm gonna take a look at a slightly harder version, going back to my PowerPoint, and I want everybody again to spend a minute to think about it. All right, and again, I want you to think about what is independence and what is not. All right, and this is the problem. So some of you might have these memorized, but think a bit about like how you might derive these. Because I personally don't really have them memorized. Every time I use them, I just think, how do I get here? And I remember this method. And I didn't give you all the information you needed. So what you're going to do is you're going to want to use the prime factorization of n and to help your answer. The answer is not n times m plus 1 over 2. That is the sum of just integers less than n. Number of divisors is going to be a bit smaller. By positive divisors, I mean all divisors. So like a positive divisor of 12, you'd include 12, you'd include 6, you'd include 4, all of them. And 1, yeah, 1's the most important one, of course. All right, great. Somebody's given me an answer to the first parts, but second part seems to be eluding. eluding all of you. And that's definitely the harder one for sure. So, all right. So I'm going to get rid of this list right now. Hopefully everybody sort of has it in mind. And let's try and solve this digit. So the first thing I'm going to do is write it in standard prime factorization. All right. So now we need to choose a factor. And the idea is that these prime, what doesn't depend on each other is going to be each primes. These primes are separate. So let's call the factor m. All right, because m is a divisor, it has to have all these prime factors. So let's say p1 to, let's call it beta. All right, I'm using Greek letters for the exponents. This is standard notation. And okay, the things above the p's are exponents. So yeah. All right. So now let's think, how are we going to get this? So notice that these exponents are more or less independent. So the main question we're going to have to ask is this. How many ways are there to pick the value of B1, beta 1 right here? We're picking the value of beta 1. And remember, our main number is n. M is a factor. I should say m is a factor. I don't know what I did. Everybody's saying the wrong thing. Wait, what I'm trying to get at is that we are trying to count prime factors of n. So m's counts should not actually matter. The number of ways to choose this is actually alpha 1 plus 1. Not beta. And the reason is because we know this is true. M definitely cannot have more primes than n. So because this is alpha 1, we can pick this in alpha 1 plus 1 ways. How many ways are there to pick beta sub 2? A2 plus 1. Right. Similar thing. And of course, you can see that we're going to continue all the way down to AK plus 1, alpha k plus 1. And this is, in fact, our formula. So let's see this applied. Let's say we wanted to find the number of factors of 12. Well, we see 2 plus 1 times 1 plus 1 is 6. And we could list them all out. 1, 2, 3, 4, 6, 12. That's 6 different numbers. All right, so now notice that, again, we've used this like multiplication principle. And the reason that we can use this is that we can treat each of these like picking beta 1, beta 2, and so on as separate problems. And when they don't affect each other, you can multiply. All right, so now the second problem, the sum of all the factors. This is definitely a bit trickier. We are recording, fortunately. Thank you for checking. So I'm going to erase all this. And this is tricky to motivate. I can explain why it works, but like you can think of it as factoring, I suppose. And again, this is motivated by the fact that these are all independent. I suppose, let's say n was a prime power. Let's just say n was equal to p to the alpha. The sum of all the factors would be 1 plus p squared, all the way up to p to the alpha. All right, does everybody see why this is the case? If n is a prime power, this is why the sum is. So now I'm going to write out the following expression, and it's going to be a long one, but does the answer to this problem work for the number 1? Technically, but you kind of had to do some stuff. Like the idea is that the product of of an empty set is 1. You could use the geometric series formula to simplify these, but I'm going to keep it written out like this. Because what I want to show is another sort of counting idea. And that is that I can get any factor from here. So let's say I wanted the original number, n. I could just take these. I could just take all of these. Think of this as like some sort of like mega massive FOIL. All right, if I wanted to get the 1 factor, I could go like this. Just pick all the 1s from each thing. If I wanted to get a factor that only had P1, I could pick P1 here and then pick all the 1s for the remainder. Is anybody confused about what I'm doing? All right. So this is the formula, and you can simplify it if you want with geometric series and all, but I would like to keep it like this because I think it illustrates the more general idea of what's happening here. So, okay. Ooh, wow, this is taking longer than I would have liked. So to finish, we're gonna do this problem. It's an Amy problem, but it's actually not that bad. Stare at it for minutes. And then we'll solve it. The number of subsets of 1 through 8 is actually equal to 2 to the 8th, not 8 squared. But there is another condition. I am not appear to be frozen, but the answer is not 1, but okay. So let's see how we'd solve this. I should keep it up here. So okay, so we're looking. So we have the numbers 1, 2, 3, 4, 5, 6, 7, 8. So these are in a set, and those are in a set. So we know that Okay, so let's say S is a good set. All right, because we're thinking constructive. We want to see what works. All right, we know that if S is a good set, S has to have at least one of 6, 7, and 8. All right, why does S have to have one of 6, 7, or 8? Because if not, then it would belong entirely in here, and it would be a subset of 1, 2, 3, 4, 5. So S needs one of. All right, can you guys apply symmetric arguments, except looking at this set? Looking at this set and knowing what we know, what does S have to have? It's the exact same principle. 296 is not the answer, unfortunately. All right, and nobody is answering the question, so I will answer it. And the reason is because if S didn't contain any of these, then it would be entirely within this subset, and that's a contradiction. All right, and what about 4 and 5? S can have 4 and 5 if it wants. So now what we've done is we've just broken it down into 3 smaller counting problems. So how many ways are there to choose the elements that S contains that belong to 6, 7, 8? And the subproblem that we are going to need is that of the number of subsets. So let's actually solve this. How many subsets are there of 1, 2, 3, 4, 5, 6, 7, 8? And this is another application of this independence thing. All right, there are 2 ways to choose whether this element is in or not, 2 ways to choose whether this element is in or not, and so on. There are 2 times 2 times 2, which is 8. However, this is not it, because we need to make sure that this is not empty. We can't have the empty set because S strictly needs one of these elements. So we actually get 7 here. I'll circle that. Does anybody have any questions as to why we have to subtract 1 from the number of possibilities of 6, 7, 8? If you do, you can ask Andrew. All right, now S needs one of 1, 2, 3, and that's 7 because these 2 problems are essentially the same. This one is unchanged. This is 2 squared, which is 4. And the reason it is because we don't care whether S has 4 or 5. So when we multiply these all together, we get 196. All right, if anybody has any questions or is the slide is a bit confused, please. Yes, I'm getting lots of messages about the Just New clone. We do know he exists. And I would rather he didn't. What does S is a good set mean? S, it just means it satisfies the given condition. All right, it's not a subset of this, and it's not a subset of this. Yeah, we are working on it. So yeah, okay, that has been resolved. So I think, yeah, we're gonna go to the next section right now. And there we go. And this section is complementary accounting. Can everybody see the PowerPoint? So we're starting with a simple example. The principle behind complementary accounting is subtract the cases that you don't want. So you're counting like two things, but usually these are a lot easier. Okay, I think the answers that I'm getting, I think they're correct, but actually I don't know. All right, this is not a probability question, so we should not have a fraction. All right, let me get a new share. All right, so the way that we're going to solve this is first we're going to count the total. So how many ways is there to flip 10 coins without any restrictions? Well, that's just 2 to the 10th. Each coin has 2 possibilities. The coins are independent. So now we are going to now we're going to subtract out the bad possibilities, because this is what complementary accounting is. So minus 9 heads, minus 10 heads. So now we have to see a related question. How many ways are there to have 9 heads? All right, this is just 10 choose 9. And here we're going to start seeing the binomials start coming in. And this is equal to 10. Yeah, there's like, you can think of it as 10 ways to place the tail. 10 heads, there's clearly only one way. So 1024 minus 10 minus 1, PEMDAS, we go left to right. This is 1013. So the alternative way is saying, oh, there's 1 head, there's 0 heads. There could be 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, and 8 heads. And then if we did that, we'd have to add this up. What do you want me to say again? I said a lot of things. All right, what we did here again is we counted the total, and then we subtracted out the bad cases. So the cases are all like 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads, 10 heads. But the ones that don't fit the question are 9 heads and 10 heads. So we just count those, and those are just binomials, and we subtract them out. Why do I do 10, 2, 0? Because what if there are 0 tails? That's a perfectly valid case. Or 0 heads. This would be tails, 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 tails. I don't write it as 1 because that way we keep like the symmetry of this expression. It looks weird otherwise. But yeah, this is the principle of complementary accounting. And we are about to see a slightly harder application. And let me share the correct thing. All right, this is an old AMC question. So to stare at it for a minute, think about what is the complementary case? This is technically not an AHSME because that was disbanded long before this problem. I actually took this problem in competition. I remember not getting it because I didn't see this nice idea. So think, what's complementary? How can we use complementary accounting? And I'm going to see if I can try and write on it. But yeah, I do not. More. Okay, so yeah, I'm going to assume that you guys have read it. And I'm just going to go straight into it. So teams won 10, lost 10. And each team. Okay, so the first question is, from the statements, can you tell me how many teams there are? All right, the important thing is that this is a round robin tournaments, which means each team plays every other team. Each team won 10 games and lost 10 games in this round robin tournament. This is definitely tricky because it's tripping up a lot of you, and that's fine. So so we know that, like, let's pick a team. Let's pick a team like A. All right, they win against these 10 teams and they lose against these 10 teams. So there are 10 teams here, 10 teams here, and one team here. A lot of people miss that. We can't forget it's the original team. So 21 teams. And this is something that the problem didn't tell us, so we had to figure out ourselves. So great job. This is a major part of the problem. So now, okay, so how many games were played in total? We're going to need this for the complementary accounting, but spoilers, this is complementary accounting. If there are 21 teams, how many games are there in total? And it's a round robin. Keep that in mind. Yeah, 210. So 210 games played in total. And how did we get 210? Well, that's just 21 choose 2. We have to choose 2 teams to play again. Yeah, so this number is actually not going to be important. But what is important is that remember that we're selecting triples. So how many ways can we select triples? How many ways can we choose 3 teams? Wouldn't it be 420? Great question. It would not be because we're dividing by 2 because it doesn't matter what order we choose the teams. Choose notation means we have 21 teams and we're choosing 2 of them. So triples are going to be 21 choose 3. And somebody compute that for me, please. 1330, yeah. All right, so wait, okay, so now I'm going to introduce you a cool way that we can compute this. So, or that we can visualize this. So like imagine that we have like a bunch of teams like here. What we can do is we can draw arrows that represent wins or losses. And the order that you choose like doesn't really matter. It all depends to you. I'm going to say that an arrow going from team A to team B means that team B beat team A. So does everybody understand this setup? We can draw arrows between every pair of teams that signal whether they won or lost games. So now what we're going to do is we're going to take a look at this situation. That's going to be confusing, yeah, but that's why we're keeping it simple. So basically this can happen or this could happen. It doesn't matter, just based off the order. But we're gonna have this. Or actually, I need to reverse these arrows according to our conventions, so. Sorry. All right, so now let's think. We're doing complementary accounting, so we want to see when this doesn't occur. So think, what arrow configurations can we make so that we don't have this sort of like cycle thing going on? All right, and I'll start drawing something. We can reverse one of them. Yeah, let's say we reverse this one. This is what we get. So yeah, so two of them are just going to A, and then the third one we don't really care about. It's just doing its thing. All right, we could reverse it in a different way also. We could maybe A loses both of these games. So yeah, so we have these possibilities. So it turns out these are a lot easier to count. Because one of these teams is special. One of these teams has something like really special coming from it. What's special about one of these teams? Actually, and I'm just gonna keep this case. I eliminated this case because it's actually the same as this. The reason is because now we had B losing to both teams. But let's say A is special. And A is special because A wins twice, and that's cool. So here's how we're going to count these triples. So let's say we have our team A. We have wins and we have losses. How many ways can we pick teams B and C so that A beats both of them? All right, because we want this situation. The answer to this question is 45, which is 10 choose 2. So there are 21 ways to pick this. And A needs to win to both of them. So these are going to have like a bunch of arrows that all point to A. And this is the number of ways. So basically what we've done is we've counted, yeah, the number of ways that we can pick this. And if we multiply this out, it works out to, let's do some quick math, 945. So now notice that what we just done here is that we just counted the number of bad triples. These triples are bad because they have a clear winner. And when I say clear winner, I mean one person who just dominates both of them. So we're going to subtract those out because we don't want that. And what we end up with is 385, as somebody in chat. So, great. So that's the answer. All right, there is a lot of like stuff going on there, but I just want everybody to remember the main idea was looking at complementary accounting. How can we rearrange these arrows so that they don't have the cycle structure here? And when we have a clear winner or a clear loser, we could have done it based off that and it would have worked out exactly the same way. And it would have been fine. Okay, so now I need to co-host Andrew because his computer crashed. So after we do that, we'll go on to the final section, which is casework. Where did the 945 come from? Great question. That is this product. 21 times 10 to 2. The 21 is the way that number of ways to pick your clear winner. The 10 to 2 is to pick the teams that it beats. Yeah, if you ask Andrew questions and he didn't answer, feel free to send them to me right now because he probably does not have them. I'm hoping that's not the case. So I'm going to share this and we're going to go on to the next question. Casework. All right, casework is everybody's least favorite thing about math competitions, that I know, and it should be everybody's least favorite thing. So that's coordinate bash. I do hate coordinate bashing, yeah, but no, but the thing is with coordinate bash, at least you can avoid it most of the time. This is more or less unavoidable. So I want to start with a silly example of casework. And the idea here is that we can actually reduce this to a very stupid type of casework. And that type of casework is called bash. All right, so arrangements that are considered the same if they differ by rotation and reflection. Chord bash is fun, lucky you. And it turns out that if we account for rotations and reflections, because reflection is just division by 2, and rotation, there are 5 different ways to rotate it, so you divisible by 5, there are only 12 different cases. So we can literally just test out every single case and see how many of them work. So I am going to go ahead and do the work. I'm going to do the work for you and write out every single case. All right, and I want you to note how I keep them organized. So 1, 2, 3, 4, 5. 1, 3, 2, 4, 5. 1, 2, 3, or actually, I'm not keeping them organized, but I know. Okay, I should be structured about this. 1, 2, 3, 5, 4. And for these, we're going to check the condition. I don't have the condition up here. That's my fault, but what is in the problem? Yeah, I'll re-explain that. Drawing these out takes a lot of time on whiteboard. 4, 5, 3. 1, 2, 5, 3, 4. 1, 2, 5, 4, 3. This is like circular permutations, except we're taking out rotations and reflections. So the way that I'm taking out rotation is that I'm making sure that 1 is always at the top. And the way that I'm going to take out reflections is that I'm going to make sure that either 2 or 3 is over here, or that the lower number is here. So I think these should all be distinct. So the lowest number in these cases are 2, and they're all on the right. So let's say 3 was here. So 2, 4, 5. 1, 3, 2, 5, 4. 1, 3, 4, 2, 5. The reason I can't have 2 here is because then this number would be greater than that number. We can't. You say 20 hours later, but we are almost done. And this would be a lot faster if you were working by yourself on the paper. I'm just being intentionally slow because I'm on a computer. I'm doing it on a whiteboard. I'm trying to be clear. But yeah. So I'm also going to draw boxes because this is probably confusing the heck out of a lot of people. And more importantly, it's confusing the heck out of me. So let's see how straight lines I can draw. So what we are going to do is, there's probably some smarter way, but But I want to illustrate the power of Bash. I also have a writing tablet, so this is like sort of doable. So what is it asking for? It's asking us to find every sum from 1 to 15. And we can cheat a little because the sums from 1 to 5 and 10 to 15 are easy. We can find a sum of 1, 2, 3, 4, 5 easily. Those are just the numbers here. All right, to find 10 through 15, we just take the complements. Say I wanted 10, I find this 5. 15 minus 5 is 10, and I just take the other ones. So what I'm going to be doing is I'm just going to go really fast and check for 6, 7, 8, or just 6 and 7. Because again, because of complements, I can see that 6 implies 9 and 7 implies 8. Understand the condition. Yeah, I need to explain that better. Basically, we want to make sure, we want to count bad ones. So good ones are if we can find every sum within looking at a contiguous sentence. So for example, we have 1, 2, 3, 4, 5 here. We can find 6 by doing this. But no matter how you circle a consecutive block of numbers, we can't find 7. So this is bad. All right, let's take a look at this. We can find 1, 2, 3, 4, 5. We can find 6 right here. And you can find 7 right here. And then you can find 8. You can find 8 here, 9 here, and then 10, 11, 12, 13, 14, 15 all work. All right, one important aspect of symmetry that I'm using is that if you can find x, you can find 15 minus x. So like I can find 1 and I can find 14 just by taking complements. So this does tie into the whole complementary accounting thing. Is this actually how we're supposed to do it? No, how you're actually supposed to do it is you're supposed to notice the symmetry. I think that helps a lot of things. This looks so bashy, but I'm going to go through all of it really quickly right now because I only need to check for sums of 6 and 7. Okay, so there's a 6 here, there's a 7 here, that's good. There's a 6 here, and there's a 7 here, that's good. There's a 6 here, there's a 7 here, that's good. There's a 7 here. Oh, wait, no, I was wrong earlier. There's actually a 7 here, so there's a 6 and a 7, so this is good. So we haven't found any bad ones yet. All right, take a look at this one, though. Can you find a 6 anywhere? A string of consecutive numbers that sum to 6. It turns out you can't. You can look all you want, but you can just see this just by looking at it. There aren't many numbers. So this is bad. All right, now let's take a look at this. Oh, we have a 1, 3, 2, so that's a 6. And then we have a 3, 4. That's a 7. So this is good. 1, 3, 2. Can we find a 7 here? There aren't any 7s. 1, 3, 2, that's a 6. And then a 2, 5, that's a 7. So that works. Yeah, 2, 4, 5, 2, 7, 6, and 7. Yeah, so you see that like I'm going through these really quickly, and I'm like taking breaks right now, but you'd see that this would go really fast. All right, it is becoming really clear to me that I will go very over if I intend to get through all these problems, because we haven't even gotten to the hard casework problems. This one I heard was good, and I do not see I see a 6. Okay, 6 and 7, that works. The rest of them are good. I do not want to take your word for that, even though I do trust you. Okay, 1, 4, 2. All right, 5, 2, 5, 1. So after all this, we found 2 bad ones, so the answer is 2. So yeah, this looked really bashy, but it actually wasn't that bad because we didn't have to do any like computations or anything that really hurts our brain. All right, all of these cases, we could just look at it and see. It's possible that there's a nicer solution, but I can't see one off the bats. And honestly, if I was doing this on a contest, this would be what I do. Is there a systematic way? This is the systematic way. This is as systematic as we can get. We're just literally listing out every single possible case, and we're just bashing them. The systematic, like you can like check like every like single combination, but that's like pretty boring and like pretty easy as you saw. But yeah, the point that I wanted to get across here is that like listing out all the possibilities actually isn't really as bad as you might think. It took up my entire whiteboard space, but that's because I can't draw really nicely on whiteboards. And like each case was not quick. Can we not go over? That's going to be impossible. So if you have to leave, I'm sorry, but I really hope you don't. So let's take a look at this question. All right, and yeah, just get the essentials written down like really quickly because I'm gonna try and go faster. This one is gonna be like a bit more refined casework, but it's still gonna look like a lot of cases. All right, this is the method that I like to use. Okay, so 6 die. Okay, 4 dice. Add to 14. And they're standard 6-sided die. So what I like to do is just basically list out all the possibilities, except they're sorted. And then just figure out how we unsort them. Didn't we do this with 6-sided die that added up to 12? Yep, but we did that with gen funcs. And I think this is slightly better. So stars and bars does actually not work here. And the reason is because if we had stars and bars, it's really conceivable that we could get a streak of 8 before our first bar, or 7 as I've drawn. And that's not possible with this setup because no single dice will have 7. So this is a great example of where stars and bars fails. So 2, 2, 4, 6, 2, 2, 5, 5, 2, 3, 4, 5, and I think this is 3, 3, 3. Yeah, this is, I think, the fastest way. Can you do stars and bars and then subtract the other cases? That's complicated casework. This is simple casework, and it's actually not that bad. I guarantee it. Because what I've just done is I've just listed all the cases. This is it. So now, okay, so how did I do this? I kept everything organized just basically by keeping everything sorted. Writing these in ascending order. And hopefully you can see the pattern for this. I'm just sort of decreasing the first one that I can. Or increasing the first one I can, decreasing the rest. Does order matter? Great question. It absolutely does. The reason that I put them unordered is that because now these are a lot smaller cases. I did not miss 2, 2, 4, 4. Do those add up to, oh, thank you. I missed 2, 4, 4, 4. Yeah. Okay, it is, I do believe that this is the best one. But yeah, thank you for catching that. I think this should be everything. So basically, we go through all of these and we count the number of ways to arrange them. So this can be done in 6 different ways. All right, and this is why having complete mastery over binomials is so important because that will allow you to do these like that. So for example, I could see that this is the 4 choose 2 setup, which is 6. This, all 4 numbers are different, so that's 24. All 4 numbers are different, so that's 24. All right, this one, we have 2 numbers the same and 2 numbers different. All right, you can arrange these in 24 ways. Divide by 2 because the 5s are the same, and you get 12. So you can basically do that for every single one of these. That you could just classify these in these cases. And if somebody eager really wants to add them up, this one's different, but it's easy. Add them up for me. I would love to not have to do this. Okay, 6, but I'll do it anyway. 78, 90, 90s, 90, 120, 128, 130. I think the answer is 134. Bye. Andrew, are you able to stay for the rest of the meeting? Because if not, it's fine. I'm going to go way over. Great, thank you. Okay, so what part did I do fast? Like the whole part about doing all of these, like figuring out all these numbers, or just adding everything up? Adding everything up, these are all multiples of 6s, so you can group these in special ways. So like 6 and 24 make 30, 6 and 24 make 30, 24, 12, 12, 12 makes 60, and adding multiples of 10 is easy. Can we not go over more than 10 minutes? I will go over as long as I think is necessary to solve all these problems. All right, a lot of these are just going to be like adding just like different ways of setting up casework. All right, how did I find all these cases so fast? This is why you have to stay organized. Yeah, this is one of those constant things that you hear and you always hate. 4 is not divisible by 6, but it's at the end. All right, stay organized, stay organized. But it was because I was able to stay organized that I was able to like figure out all these cases so fast. I start with like the most extreme one, where like all the small ones right here. Then I get incrementally bigger. Just like I can increment this one slowly, make sure that here works out, and then just keep going, keep going, keep going. And with enough practice, you can all do this too. I'm confident in that. So just try and like think about this method. Write out all the cases that are sorted, then figure out the number of ways to arrange them, then add them all up. And do this example problem too. It's complicated enough so that you should be able to work through the solution. So let me go to share the correct thing. Here is our next casework question. All right, and this is actually a bit of a notorious question because it was in a 2017 Math Counts Nationals. Question number 29, only one person in the entire nation solved it correctly. And I am lucky because that one person is the TA for this thing, so he can yell at me if I got it wrong. Can people see the screen? That's weird. Oh well. But okay, I'll restate the problem. Haha. You can see the chat. All right. How many people have that? Oh, that's strange. I don't really know how the screen sharing works, so. How many people tried this problem? A lot of them, probably. I mean, I don't really know. The third sentence. The sum of the possible. Oh, that should say the. I'm sorry. Sorry, I will fix that in the handouts. So, yeah, let me pull up a whiteboard and we'll get started. So, yeah, part of the reason that a lot of the top people got this wrong is that the casework is really tricky. So there are two conditions. So the way that I'm going to keep this like be extra careful, and this might be a bit longer than possible. The answer is a lot bigger than 12.75. Let's say these are the 3 pieces of the rope, and these are in order. So we have 2 conditions, +5 and ×2, and I'm gonna have to write that on the side. And actually, nah. I hope this works out. And a lot of these are going to be overlaps, but I honestly do not care because we're going to be paranoid. I do not want to miss a single case. And this is tricky enough. So this is one of the questions that I did memorize the answer beforehand. So I'm setting up this table. And again, there are a lot of possibilities. So the upshot of this is that we are going to solve nine different systems of equations. But because they are all really similar, they should all take around the same time, and they can become practice. And we are just doing casework on where each of these conditions applies to, because we know they have to apply to some pair. So let's say, okay, so this main diagonal is interesting. All right, let's say that we have A, B, that B is equal to A plus 5. That's this condition right here. So that's going to be this row. And C is equal to, B is equal to 2A. We can solve this pretty easily. And this is not like interesting. And this is also why I impose this order A is less than or equal to B is less than or equal to C, so that I know that it's not the other way around. All right, if this is the case, then we have A equals 5, B equals 10, and can somebody tell me what C is? C is 21. Or wait, what? C is 17. Well, or oh wait, no. I copied that down the problem wrong. I am sorry. These sum to 36. Yeah, so it is 21. So that's one triple, right? 5, 10, 36. No. Perfect. So we've done one case. Now there are only 8 cases left. So now the next case is, what if C is equal to A plus 5 and B is equal to 2A? So that's going to be this box right here. If anybody is confused about the way that I'm doing these, that I'm arranging these cases, or the way that I labeled this box, message me and then I can clarify. So when we plug these in to here, what do we get? We get the equation 4A plus 5 is equal to 36. So yeah, A is 31 over 4. It is okay that A is not an integer. It asks for a decimal to the nearest tenth, so we sort of expected this. So in that part, I'm going to break my moral code and write this as 7.75 because I think the decimals will just be easier. So A is 7.75. B is going to be this times 2, so that's 15.5. And C is going to be, ooh, this is interesting. C is going to be 12.5. This is a contradiction because we have this condition. So B cannot be 2C because B is less than or equal to C. So this case is actually invalid. And we're going to get to this later, and maybe you could do some smart stuff to not have to do it again, but I don't care about being smart. I care about being correct. All right, so the reason I just blacked out this case is because we got that B was greater than C, and that's a contradiction to this assumption right here. So it's gonna, I'll just do the work here. It's gonna turn out that this is 7.75, and then 12.75, and then 15.5. I think I got that right. And that's just because I swapped B and C. On that matter, while we're knocking out obvious cases, this case can also be knocked out, and this case can also be knocked out because they're more or less permutations of what we have right here. Is anybody confused about what I'm knocking out? So please message me. All right, so the final case, BC. So C is going to be equal to B plus 5. and B is going to be equal to 2A, just like before. So we're doing this one right here. So let's plug this into this equation again. All right, we get, I think, 5A plus 5 is equal to 36. Then A is going to be 6.2. B is equal to 12.4. What is the amount of time to solve this in nationals? Much less than what I'm doing right now, but I'm also explaining, taking the liberty of explaining. Then C is going to be equal to, I do hope I'm doing this correctly, but I'm taking extra care to keep myself organized. All right, so we can already sort of see that this 21, the 17.4, this 15.5, those are all going to be added in our sum. So you can just sort of get an idea of how big the answer might be. All right, great. So am I going too fast on the solving of linear equations for anybody? And please let me know. Please be honest if that's the case, because this is the boring part. I'm perfectly fine to skip steps, but if you don't know what exactly I'm doing, then I can slow down a bit and explain them. So, okay. So we're going to go on to this case right now. All right, and plus 5, so that's C is equal to B plus 5. But now C is equal to 2A. Interesting. So instead of this B, we have C. So that's this right here. So now in this case, I think it's a bit more practical to solve for C in here. So that's going to be 5C over 2 minus 5 is 36. So 41, so 82 over 5, what is that, 16.4? A equals 8.2, B equals 11.4. That's another one. It's 4:13 p.m. already. Yes, I planned way too many problems for this. We haven't even gotten to like the last two, which are going to take at least as long. I might end it early, but I want to show you these because these are like good extreme examples, and counting can take a while sometimes. So estimating, I think this is about right. And I think we might actually be done because if we switch the variables, if we switch B and C, that's equivalent, like that's equivalent to like moving to these two. And they can't, that would be the same thing as switching these, and we can't do that. So I think we're done. And let me just check that 21, 15. Let's add these up. 21, 15.5, but okay, this is not the correct answer. 0.3, 1. All right, 2 plus 5 plus 7 plus 6, that's 0. 4, 5, 6, 7. So we're at 70.3 right now. Thanks. Which problem is? All right, okay, so so I think we do need to do one more of these cases because, yeah, that makes sense. So, and this is why we should be diligent. And like crossing things out is like no good. So we're gonna do both of these. So I'm gonna keep our current total is 70.3, but I'm gonna get rid of all the equations and clean up all computations. All right. If you were doing this in the actual national test, it's possible that you wouldn't have a lot of time left and you might try and make some shortcuts, and that's probably why so many people miss these questions. I want to instill good habits, so I'm going the long way. Okay, so this. B is equal to A plus 5. C is equal to 2B. Oh, I know. I put this case over here. No, no, I didn't. I did something else weird. So C is 2a plus 10. We have 2a plus 10, a plus 5, and a. So what do we end up with? 4a is equal to 21. So a is going to be 2a is going to be 10.5. Oh, yes. Yeah, this is the one case we're missing. This does work. So I think this works as 5.25, 10.25, 20.5. So we add that to here, and we get 90.8. And that's actually the answer. C is not equal to 11 in this case. All right, so in this case, what we're doing here, you got that A is equal to 5.5. But C is equal to 2B instead of 2A. And that's tricky. So you have to yeah, it's so important to be careful. Okay, in this case, you had the same equations as me. You didn't plug it in correctly though. B is equal to 10.5, so you plug that into here. Is 5, 10, 21 really valid? It absolutely is. Yeah, this piece is 5 inches longer and twice as long. How many problems left? I'm thinking this might be the last one because otherwise I have 2 and they're gonna both take a while. Yeah. Okay, this one, let's just do really quickly. Let's just say, okay, A is equal to, A plus 5 is equal to C, and 2B is equal to C. And from this, I can sort of see that I think that B is going to be greater than A, which is a contradiction. So it turns out that this is also a bad one. Can we do one more problem? We're already really over right now, and I'd rather not push it. And I think this is a good one to end at. So, all right, what did we do here? All right, and I'm just saying, if you really want me to end now, you could just not come. Nobody's stopping you from getting out. All right, now. So what do we do here? All right, so we impose this order so that we could get some sort of structure on the 3 pieces. And then we just did casework on literally every single pair for which these conditions could apply to. All right, and this ensured that we captured everything, but it also meant we caught some bad cases, cases that just don't make sense. That's these black squares right here that we had to cross out. But doing it in an organized way, like this table that I did, made sure that we didn't. Move on. I will be going to MIT when I enter college, yeah. So, yeah, I think that's everything I have for you. There'll be a couple of other bonus problems on the handout that we might write up. But yeah, they're definitely difficult. Hope people